Here at the Royal Institution, we believe that science shapes our lives, our culture, and the world around us. For more than 200 years, we have been creating opportunities for everyone to discover, discuss, and critically examine science through our innovative public events, world-famous Christmas lectures, YouTube videos, and cutting-edge education programs. Become a member of the Royal Institution today and help us to inspire everyone to think more deeply about science and its place in our lives.
Hello everyone, I'm Martin and I'm the Public Programme Manager at the Royal Institution, and it's fantastic to have you along for tonight's stream. It's going to be absolutely brilliant. I'll be introducing your speaker, Brian Christian, soon, but just to mark your card for future events, don't forget on Tuesday next week, we've got Rohin Francis, who some of you might know as Midlife Crisis, and he'll be asking, how far can you push the human body? And then don't forget on Thursday next week, we've got the fantastic neuropsychologist Mark Solms, who'll be delving deep into the mystery of consciousness. So I don't think you'll want to miss either of those, to be quite honest. Before we get underway, I'd like to welcome our members and patrons. If you don't know, anyone can join the Royal Institution. I'd strongly recommend that you do. There's no qualifications, no nominations. You just need to like science, like us, want to support our work and want to see more of what we do. So please do sign up as a member. You get a lovely membership card as well. I'm a member of the Royal Institution. Albert Einstein was a member of the Royal Institution, Faraday, and many more brilliant people. So yeah, we're really grateful of your support in these really tough times. If you haven't seen it already, there's a chat box on the right-hand side of the YouTube page. It's really lovely, actually. Lots of people have been saying hello and saying where they're from. I think we've had Sacramento and Guatemala and quite a few people from Surrey. So a real range, to be honest, but it's lovely to see you all. Don't forget, please type any questions, comments and stuff you're thinking into the chat box. We'll be monitoring it, and at the end, I'll take some of those questions and put them to Brian after he's finished his presentation. Yeah, and please be nice. Everyone's normally really nice, but I just have to say be nice. Thanks. There's also be links to purchase copies of Brian's book that will be popping up throughout the evening. So do click those if you can. They'll take you to your local Amazon store. So if you're in Guatemala, I assume it'll take you to Amazon Guatemala. But of course, we do know that Amazon has been doing particularly well during the last year of coronavirus, whereas independent local bookshops have not been doing so well. So if you do, if you would like to go out and support your local independent bookshop, we would fully support that decision. Yes, and unfortunately, like small independent bookshops, small independent science charities like the Royal Institution have also been having a bit of a tough time. You may or may not know, but we're completely independent of government. We don't get any funding at all from gov.uk. So it means we have to kind of make our own way in the world, which is good because it means we've got independence, we've got freedom, we can do what we like, but sad in that we have to raise all our own money. And previously we did that with hiring out our building, running events, doing all kinds of great stuff. Loads of people from the BBC, London Fashion Week, all kinds of people would hire us out. Sadly, they're not doing that at the moment. So we're a little bit short of cash. So therefore, there is a suggested donation for tonight's event, if of course you can spare it, because I know a lot of people are having financial difficulties as well. But if you could spare us a donation of £10 or more, we'd be more than grateful for your contribution. We also send, as usual, send out a survey after the stream. So if you could fill that in as well, that would really help us know who's out there, who's watching, and what sort of stuff you like. Well, that's probably enough of me jabbering on. So it's time for me to introduce your speaker, Brian Christian. He's the author of The Most Human Human, which was named a Wall Street Journal bestseller, a New York Times Editor's Choice, and a New Yorker Favorite Book of the Year. Also, he gave a talk on that book at the Royal Institution back in 2012, which I still remembered when his publicist got in touch with me to say, have you heard of Brian Christian? I had to say, yes, his last talk was brilliant, albeit 8 years ago. So it's really fantastic that we're able to welcome him back. He's also authored with Tom Griffiths, Algorithms to Live By, which was a #1 Audible bestseller, an Amazon Best Science Book of the Year, and MIT Technology Review Best Book of the Year. And his third book is called The Alignment Problem, which he'll be speaking about tonight and is published this year. Brian's from Wilmington, Delaware, And we had a bit of a chat about other famous things from Delaware and what Delaware is known for. So if anyone out there is from Delaware, do let us know in the chat. He holds degrees in philosophy, computer science, and poetry from Brown University and the University of Washington. He's a visiting scholar at the University of California, Berkeley, and lives in San Francisco. So without further ado, joining us live from San Francisco, can you please give a big virtual welcome to Brian Christian? Thank you.
Thank you so much, Martin. And it's a real honor to be able to speak to the Royal Institution members again. I believe that the development of machine learning over the last 10 years in particular has brought us to a critical juncture between computer science and ethics, and raises what I think will be the defining human scientific project for the coming decade, if not century. But the story of this moment that we find ourselves in now really begins 86 years ago. It's 1935 in Detroit, Michigan, and someone named Walter Pitts is running down the street, chased by bullies. He ducks into the local library to take shelter, and he hides. In fact, he hides so successfully that the library staff don't realize he's in there, and he's locked in the library overnight. While he's in there, he finds a book that catches his interest. It is the 2,000-page treatise on formal logic, the Principia Mathematica, by Alfred North Whitehead and Bertrand Russell. Walter Pitts reads it cover to cover and then writes a letter to Bertrand Russell saying he believes he's found several mistakes in the text. A few weeks later, he gets a letter postmarked from England. It's Bertrand Russell saying, "Mr. Pitts, I have no idea who you are, but you are welcome to come join me at Cambridge and study with me as a doctoral student." Unfortunately, Walter Pitts must decline the offer because he is 12 years old and he's only in the 7th grade. Now, several years later, he gets word that Bertrand Russell is coming to Chicago to give a talk. He's so excited that he runs away from home at the age of 15. And in fact, he never returns. Pitts ends up living as a teenager for many years, homeless in Chicago, working menial jobs and dropping in on lectures. Finally, he ends up meeting someone who will change his life, and that is the esteemed neurologist Warren McCulloch. The two of them form a friendship that is almost familial. McCulloch becomes basically a father figure to Pitts, and Pitts moves into McCulloch's basement. And that year, in 1941, the two of them regularly stay up, until midnight talking. The brilliant teenage logic prodigy and the esteemed mid-career neurologist. And they start thinking about whether their two fields can be reconciled. Could we actually think of the brain in logical terms? They come up with this very simplified model based on what was known about neurons at the time. You could imagine it mathematically, they think, as being this very, very simple machine that takes in these numbers as input, and if they're above a certain threshold, it will emit a number as an output. Otherwise, it does nothing. Gradually, they start to realize that a network of these artificial neurons, suitably wired up, could compute anything that could be computed with Boolean logic. Of course, it is far from simple exactly how the wiring up should be achieved. Now, they saw their project as perhaps an investigation into the nature of the brain itself. And to Pitts's, I think, sad disappointment, turns out the brain is in fact nowhere near so simple. But they had also done something else in those late night conversations in 1941 and 1942, which is to begin this, I think, defining human project of trying to actually build systems out of these artificial neural networks and see just what such systems could do. Now, people who are familiar with the history of neural networks know that it has a famously uneven history over the 20th century. There are many waves of excitement and these sort of cycles of boom and bust. But I think all of that changed decisively and I believe permanently on Friday, October 12th, 2012. at the ImageNet Large Scale Visual Recognition Challenge, which that year was being held in Florence, Italy. It was a competition between a number of different groups to identify and recognize and categorize images using computers. And it was this year, in the fall of in October of 2012, when neural networks made their final, I would say, triumphant return. A team from the University of Toronto, led by Alex Krasevsky, ended up getting, as you can see, half the error rate of the previous year and of the next best team that year. And if you take stock over this 8-year span from 2010 to 2017, you can see that there's a real revolution that begins with deep neural networks that continues all the way to the present. And in this case, we can see it represented as the error rate in this image recognition task dropping by tenfold over an 8-year period. And we find ourselves now at the present really living in a transformed world. In fact, in 2021, you can't even take a photograph without, in this case, if you use an iPhone, there is an 11-step machine learning pipeline that's happening under the hood. Right when you press the camera button, it is doing the exposure, the white balance, the focus, noise reduction, et cetera, all using deep neural networks that are essentially calculating what they think your camera is seeing and how they think it should look based on what they think it is. Now, there is a second trend that I think is less celebrated than this explosive growth in deep neural networks over the last 10 years, but I think is equally, if not more important. And that's the way in which machine learning systems, some of them much simpler than this, are working their way into the decision-making infrastructure of society. So here's a look at the number of states in the US that use statistical or algorithmic risk assessment scores to determine whether people are released from prison on parole. And you can see that there is this huge discontinuous exponential curve that happens at the end of the 20th century. And we all know where that has gone in the last 20 years. It's only up. In fact, just a few years ago, when the US Supreme Court Chief Justice John Roberts visited Rensselaer Polytechnic Institute, he sat down and spoke with University President Shirley Ann Jackson, who asked him, can you foresee a day when artificial intelligence is a part of courtroom fact-finding, or more controversially, even judicial decision-making? Can you foresee a day when AI is a part of that? And he responds, yes, I can foresee it. It's here. And so on both counts, we really are at this moment at the intersection of these two trends. On the one hand, machine learning systems that are trained by examples rather than being explicitly programmed are dramatically lurching forward in terms of the actual capability of what they can do. And at the same time, these sorts of systems are percolating further and further into the actual decision-making apparatus of society. Whether you get a loan, how you get diagnosed for disease, whether you are given parole or released pending trial, et cetera, et cetera. And so on both of these counts, a large number of people in the last 5 years, let's say, have started to get concerned. Now, these concerns about whether these machine learning systems are really learning what we think they're learning, or really going to do what we think they're going to do, they're hardly new. In fact, they go back to some of the earliest pioneers of the field. This is Norbert Wiener, the MIT cyberneticist, who wrote an essay on the moral and technical consequences of automation in 1960. He writes, "We all know the fable of the sorcerer's apprentice, in which the boy makes the broom carry water in his master's absence, so that it is on the point of drowning him when the master reappears." Some of us know this as the Goethe poem. Some of us know this as, the Mickey Mouse Fantasia animated short from the early 20th century. It's the classic fable of be careful what you wish for, right? Well, Wiener writes, disastrous results like this are to be expected not merely in the world of fairy tales, But in the real world, if we use to achieve our purposes a mechanical agency with whose operation we cannot efficiently interfere once we have started it, then we had better be quite sure that the purpose put into the machine is the purpose which we really desire, and not merely a colorful imitation of it. Now, this fear, this concern, has gone really from being this kind of intellectual thought experiment to being something very firmly rooted in real world examples of machine learning systems going wrong. And this problem that Norbert Wiener articulates in 1960 today goes by a different name. It's called the alignment problem. And we are really seeing, I would say, the equivalent of someone breaking the glass and pulling the fire alarm in the field of AI and computer science. These concerns about ethical and safety issues have, in a remarkably short time, gone from being sort of marginal and to some extent taboo to comprising, I would argue, the central concerns of the field of AI. And if the fire alarm has been pulled, then we are now fortunately living through the time when the first responders, so to speak, are on the scene. There has been an explosion of nonprofit groups, research laboratories, corporate safety teams. There is a first generation of PhD students graduating with computer science doctorates explicitly focused on the questions of ethics and safety. And so I set out to tell the story of the beginning of this movement. And that's really the story that the book tells. And I end up doing about 100 interviews with people all across the sprawling frontier of the alignment problem and trying to share their stories. So because we only have 1 hour together, I won't be able to tell you all 100 of those stories, but I wanted to share at least a few to give you a feel for all of the things that can and increasingly do go wrong in machine learning systems, and also the incredible interdisciplinary movement that is mustering in recent years to address that. So broadly, if you're building a machine learning system, a system which learns by example rather than being explicitly programmed, there are two main components to how this system is built. The first is the training data. What is the set of examples that you're actually using to teach it? And the second is, what is the objective function, as it's known? The way that you explicitly specify what it is that this system is trying to do. Now, in each case, there's a set of things that can go wrong and a frontier of research on trying to address that issue. So we're going to look at each in turn. For starters, let's look at the training data. To illustrate some of the problems of what can go wrong with training data, there's a story that I think is well known certainly within the world of machine learning. It starts in 2015 with the software developer Jackie Alcine. He has heard that Google Photos has just released this new version of their app using deep convolutional neural networks to automatically group photographs and give each one a thematic caption. What he sees ends up being one of the kind of most iconic catastrophic failures of image recognition that we've seen so far. The system has found an album of selfies that he took with his friend, and it has given it the caption "gorillas." So cases like this, I think, have really started to wake up people who work in AI and machine learning, and there has been a real reaction to that. So I think of people like MIT's Joy Buolamwini and Timnit Gebru from Microsoft Research and Google Brain, who have really done some pioneering work on looking at the data sets that actually get used by commercial face recognition software and showing how error rates are wildly disparate across different skin types and also gender. So here you can see some of their work from 2017 and 2018, where they showed that facial recognition systems of the time we're getting, in some cases, a 10-fold higher error rate for people with darker skin relative to people with lighter skin. And this has kicked off a very strong reaction and a strong response from industry itself to think much more carefully about how these systems are calibrated, how they are tested before being released. It's also, I think, indicative of a real sea change in the way that academic research is progressing. So there's a famous data set called Labeled Faces in the Wild that's been used by many, many researchers. And it was gathered from news articles in the late 2000s. Now, if you look at the actual paper that came out when the data set was released, it says, quote, "This data set clearly has its own biases. For example, there are not many images which occur under very poor lighting conditions. There are a very few number of side views of faces as well as views from above and below. However, the range and diversity of pictures present is very large." Well, there's been a bunch of research on exactly what ended up getting into the labeled faces in the wild data set. And not long ago, some researchers from Michigan State University were able to conclude that the data set is in fact 77% male and 83% white. And because it is compiled from people who appeared in news articles in the newspaper in the late 2000s, the single individual who is the most represented in the data set was then US President George W. Bush. In fact, there are, as it turns out, twice as many images of George W. Bush as there are of all Black women combined. Well, not so long ago, about a little bit over a year ago, a warning label began to appear on the labeled faces in the wild data set saying, many groups are not well represented. For example, there's very few children, there are no babies, there are very few people over the age of 80, and relatively small proportion of women. In addition, many ethnicities have minor representation or none at all. And I think this is such an interesting juxtaposition, and I'm putting this out not to critique the people who built label faces in the wild specifically, but to just illustrate what I think has been a sea change in the way that academic researchers think about their data sets. In 2007, when we used words like diversity or bias, we were talking about lighting and we were talking about the pose of the subject. And today we are talking about these demographic considerations. And this is not just an issue in the sort of present day ethics and in these kind of representational harms, but it's also a question that is increasingly troubling people who are thinking about physical safety with respect to AI systems and looking into the near and medium term future. So this is the head of AI at Tesla, Andrej Karpathy. And I'm borrowing a slide from him to illustrate the change in his lost sleep. So when he was a PhD student, 95% of the sleep that he lost in those days were about the algorithms that being used in machine learning. And these days, running Tesla's AI division, 75% of his lost sleep is about data sets. And it turns out that considerations of representation in data sets are sadly very important in the question of self-driving cars. So in 2018, the self-driving car from Uber struck and killed the pedestrian Elaine Hertzberg, who was crossing the street in Tempe, Arizona. And there are many, many contributing factors that led to this crash. We'll get into some of them. But one of the biggest ones, as it turned out, according to the analysis done by the National Transportation Safety Board, was that the data used to train the model did not include examples of jaywalking. All of the examples of pedestrians crossing the street that were used to train the car were pedestrians crossing at crosswalks or crossing at intersections. And so the model, in some sense, simply didn't consider the possibility or couldn't conceive of the idea of someone crossing in the middle of the road. And so here's a case where something being absent or underrepresented in a data set actually costs someone their life. So what can we do about this? Well, I think it's very important to think about the way that these data sets are composed. It's important to think about the actual human teams behind these data sets and who those human teams comprise. But what do you do if you have a model and it's already been trained and you don't know what data it's been trained on? Is there still a way to try to figure out after the fact whether there's some kind of problem or issue in the data? Well, it turns out that there's an increasing wealth of tools that enable you to do just that. One of the people I think is really done some foundational work in this is Chris Olah, who leads the Clarity team at OpenAI. And he has done some work where you can take an image classifier and ask it to essentially produce a super stimulus image. You give it a bunch of static and you say, make this static look more and more and more like an anemone fish or a banana or a parachute or a screw. And you can look at the images that it produces and use that as a kind of sanity check on, do these categories seem to represent what we think of when we think of these concepts? And in these 4 cases, I think the answer is that they basically do. But here's an interesting one. Ola and his collaborators took a look at one of the computer vision models being used at the time, and they asked it to output its super stimuli for the concept of dumbbells. They noticed something weird, which is that all of the dumbbells come with this flexing arm attached. This sort of disembodied, muscular, almost Salvador Dali-esque arm sticking out. Well, the model has learned that dumbbells are often found at the end of a flexing arm, which is certainly true enough. But that tells us that perhaps the model won't be as good at recognizing a dumbbell that appears on the ground or on a rack. So you can generalize from this to a setting in which that ends up actually being a problem. Now, some of these cases can be quite subtle and involve all sorts of cross-cultural issues. Someone, again, who has done, I think, some really seminal foundational work in this area is Google's Bean Kim. She's developed a method called TCAV, which, without getting into undue technical detail, can basically show you how different high-level human concepts are integral to the model making a classification in a certain category. So if we look at the category of zebra, we can see that stripes are very important. Something looking like a horse is very important. The background of a savanna is, fairly important. That all sounds reasonable. It suggests that a zebra not on a savanna might be harder to recognize, but overall that looks okay. What about the category of doctors? Well, using some of the major commercial and academic data sets or models, I should say, she finds that a white lab coat is important, a stethoscope is important, and also the concept of being male turns out to be important. So here's again a case where there's some indication that the model's going to be less reliable when it's looking at a female doctor. Now, some of these can be quite surprising and subtle, I would say. One of them, which is one of my favorite examples, is the concept of fire truck. So Kim's research showed that the model placed a high importance on the color red when it was recognizing something as a fire truck. Now that seems, from my perspective as an American, reasonably intuitive. Fire trucks are almost all this kind of uniform red color, red and chrome. In the UK, as I understand, fire trucks are also very frequently red. But this is not the case in Australia, where fire trucks are typically white and sometimes neon yellow. So again, this suggests that a model that puts a high emphasis on a fire truck being red in order to even see it as a fire truck might not be safe to deploy down under. This is something which, again, I think cuts across a wide swath of researchers, people who are focused very much on present day systems and people who are looking further out to things closer to so-called artificial general intelligence. And one of those people is Dario Amodei, who has led the safety team at OpenAI in San Francisco for many years, and is the author of this very seminal article called Concrete Problems in AI Safety. One of the problems that he identifies as one of the crucial alignment problems for the field is what he calls robustness to distributional shift, or robustness to distributional change. And that's the idea that some systems might be trained on a given data set, but for a number of reasons, find themselves operating in an environment that looks different than that. Now, all of these, all of the work that we've discussed so far, thinking about, more carefully vetting what goes into a data set, using these kind of transparency and interpretability methods to pop the hood of a model after it's been trained, all of that is part of the picture. But ideally, we want as a kind of backstop is a model that could itself identify when it's operating out of its training data and doesn't know what to do. I think this is a crucial human ability to know when you don't know something, and to then respond accordingly. There's been a lot of really encouraging computer science work here. So Tom Dietrich from the University of Oregon has done a lot of work on what he calls the open category problem. So for example, if you have a model that's categorizing something as one of 20 different dog breeds, well, what do you do when you show that model a glass of water or a ballpoint pen? There should be some way for the system to know that its categorical schema doesn't encompass all of the things that exist. And in fact, the vast majority of things that exist are not in any of those categories at all. And that work, I think, has been very encouraging. Another researcher who I think has contributed a lot in this area is Yaron Gall from Oxford, who has done some work on getting models to output precisely calibrated measures of their own uncertainty in sort of percentage terms. And I think these uncertainties allow models to then potentially defer to a human and say, well, I think it's maybe, I think I'm seeing maybe a dog. I'm not really sure what I'm seeing, but I'm not comfortable making a decision here. And they can sort of defer. Another person I think has done some really groundbreaking work is Victoria Krakovna from DeepMind, who has done has made a lot of strides in formalizing a system's sense of the impact of the action it's about to take. And I think these two things connect very intimately. That the more uncertain we are and the higher impact the action is that we're about to take, the more that we should step back, think, perhaps not be too hasty in making a judgment. Now, this is something that has come up in the human on the human side. How do you connect the impact an action might have with your degree of uncertainty in making it? And this is something that comes up, for example, in the medical ethics literature. What would you do if you had a patient come in with a tattoo that said, "Do not resuscitate"? But the patient's unconscious. And so you can't ask them whether the tattoo was the result of losing a drunken barbet or reflects their sincere wishes. Well, this exact scenario happened to the University of Miami, Dr. Gregory Holt. He said, it's something that any medical ethics researcher has thought about, but you never expect it to actually happen to you. So what do you do? This is also something that comes up in the law and in legal ethics. For example, in the question of preliminary injunctions, or the notion of irreparable harm. So sometimes a judge will issue an injunction that says, you need to stop what you're doing before we even determine whether it's bad, because the harm, if there were harm, is so irreparable. So legal scholars like Cass Sunstein have been thinking about that and trying to articulate the norms in those situations. And in academic ethical philosophy, there has been a boom really in the last several years of thinking about what's called moral uncertainty. And Will MacAskill from Oxford has done a lot of work here and in fact just published a textbook on it, the subject. What do you do if you're trying to act ethically, but you don't know which ethical system is even right? Are you a utilitarian? Are you a deontologist? Or do you believe in virtue ethics? What action do you take as a concrete matter when you know that you don't know what's right? I think this ends up being one of the foundational questions in human ethics. And it has been fascinating and generative, and I think a real statement about the moment that we find ourselves in scientifically, that these very same questions are now coming to the forefront of how our machines should behave. So the second area that I want to talk about is, rather than the training data, the set of examples that go into the system, um, what what is the objective function? What is the actual mathematical articulation of what it is that we want the system to be doing, or what it is we want it to be learning from these examples? That turns out to be every bit as complicated, and have every bit as many cautionary tales. One of the ones that I think is kind of the canonical in this area comes from the journalist Julia Angwin from ProPublica. She did a study on the criminal risk assessment scores that are being used throughout the criminal justice system in the United States in particular. And there's one in particular that she studied called COMPAS, which is used very widely in many states. And she and her team conclude that there are these systematic statistical disparities in the way that risk assessment scores like this, in the effects that they have on Black defendants versus white defendants. And this has kicked off an enormous technical literature as well as a public policy conversation. As it turns out, it really comes down to, how are you articulating the notion of fairness in mathematical and statistical terms? So people like UC Berkeley computer scientist Moritz Hart have articulated the different statements of fairness in statistical terms that one might use. So, for example, one might use what's called calibration by group, which says, if you are given a risk score of 8 out of 10, let's say, you are just as likely to actually go on to, be rearrested as someone else who was given an 8 out of 10, regardless of, in this case, which racial group you're part of. And it turns out that this notion of calibration, that an 8 is an 8, or a 2 out of 10 is a 2 out of 10, regardless of your race. This has been essentially the standard that's been used by criminologists for many decades. But increasingly, people are looking at these alternate formulations of fairness. So, for example, something like what's called equalized odds or equalized opportunity, looking at for example, the error rates. So for all of the people who were miscategorized by the model, are they miscategorized in the same way? And here's where you start to find big discrepancies, at least in the US. Black defendants that are miscategorized by the model are twice as likely relative to white defendants to be incorrectly judged as more risky than they are. Whereas white defendants that are incorrectly judged by the model are twice as likely to be miscategorized as less risky than they are. Okay, so we now have this plethora of different formal notions of what fairness might mean, or different ways of kind of operationalizing these ethical intuitions that we have. So we can ask a very simple question. Well, can't we just design a system that can meet all of these definitions? Well, this has been very widely researched among computer scientists and statisticians. John Kleinberg from Cornell, his colleagues, Alex Choldachova from Carnegie Mellon, Sam Corbett-Davies from Stanford. And unfortunately, the answer is no. As it turns out, you statistically, mathematically cannot satisfy at the same time these different, seemingly equally desirable notions of what makes a system fair. And so what do? Well, at this point, there's really a conversation that shifts from the computer science community to the public policy community. And it becomes, I think, a political and a public policy conversation of which of these different competing definitions is closer to the heart of what we mean by fairness. What is the space of trade-offs that we can make, and what are our priorities within that space? But I think even as that conversation begins to happen, there's a set of arguably even more foundational, fundamental questions that we can ask about the role that these risk assessment scores play in the criminal justice system. For example, what is it that we're actually really measuring and really predicting? Well, the idea of these systems is to predict whether you're going to recidivate or reoffend. So, for example, if you are arrested for a crime and your trial date is set, let's say, 2 months into the future, there is this very typical decision that needs to get made of, are you released for those 2 months, or are you held in jail for those 2 months pending your trial. Well, one of the big considerations that gets made is how likely are you to commit additional crimes in that period? And that's, in large part what these models are designed to predict, but that's not what these models can actually measure. All they can measure is whether someone was rearrested. So they have no idea if the person committed crimes or not. And it was very interesting for me. I did a bunch of archival research into the now 90-year history of using statistical models in risk assessment. And it turns out that if you go back to the 1930s, it was the conservatives that were arguing against these models. So this is Elmer Schnackenberg, a Republican from the Illinois State House, who writes in the Chicago Tribune, now wait a minute, because a parolee isn't caught committing a crime during the first or second years of his parole, he is listed during those years as having made good. So this is getting entered into the database as someone who behaved well. And not only are they, allowed to remain free, but the model is going to start learning that people like that should also be released. And so he's saying that's not fair. Just because you're really good at committing crimes and not getting caught doesn't mean we should be releasing more people like that. Well, nowadays, you hear the same critique articulated in the other direction. It's often the progressives, the people on the left, arguing, now, wait a minute, just because someone is wrongfully arrested or wrongfully convicted, not only are they going to be incarcerated unjustly, but they are getting entered into the database as someone who reoffended. And the model is then going to start recommending detaining more people like that. And so in both cases, you create this really problematic, potentially feedback loop. And it's interesting to me to see how, in this case, the political valence has flipped over the last century, but it's the same critique. And that critique is, you're not really measuring the thing that you're trying to predict. Now, I think the other question with models like this is that the training data are often referred to as the, quote, ground truth, unquote. But again, we can't, in most cases, actually measure the ground truth. And this is something that comes up not just in the criminal justice sphere, but also in image recognition. So this is Andrej Karpathy again from Tesla. Back in his days as a, in his days as a graduate student, he made himself the human guinea pig for the image recognition task and forced himself over a period of weeks to learn how to categorize different types of mushrooms and different types of cars and flowers and cats and dogs. And, it was mind-numbing work, but as he proudly points out, he was able to get up to a 95% classification accuracy after about 2 weeks of work. But wait a minute, we might ask, accuracy with respect to what? The way that the model was trained was based on categorizations made by random human volunteers and people who were paid through Amazon Mechanical Turk to, click on pictures of flowers, et cetera, for, pennies a click. All the model knows is what those people said. And so for Karpathy to say, I've reached 95% accurate on this task, he's not accurate with respect to the truth. He's accurate with respect to the consensus, which is potentially very different. If everyone thought that a baby tiger, for example, was a kitten, then that's all the model could possibly know, is that people called it a kitten, and the model would be none the wiser. This is something that's been brought up by as a potential ethical issue by people like Kate Crawford from Microsoft Research. So it turns out that not only are there flowers and dogs and cats and so forth in the ImageNet data set, but there are these categories like failure, loser, non-starter, unsuccessful person. And workers on Amazon Mechanical Turk were asked to click pictures that they thought looked like losers, and the model built up this category that it could recognize a picture as a loser. But what does that even mean? What are we training these models to do other than to internalize and potentially recapitulate human stereotypes? And so Crawford's work and others has caused a dramatic reevaluation. A lot of these categories have been purged out of the data set as a result. In thinking about the criminal justice setting, I mentioned that these models are often used for pretrial detention, predicting whether you're going to reoffend, and if so, recommending that you're detained pending your trial. the models are explicitly designed not to be used for sentencing purposes. And yet many of them are anyway. And there are examples of judges saying, well, this risk score sheet here says that you're a risky individual to society. Therefore, we're going to lock you up for the maximum sentence. And that is, again, explicitly what the model is designed not to do. And so I think the time has probably come for something in machine learning ethics equivalent to what we have in medicine, of a giant label that says, important, use this exactly as directed. It's also important to think about the difference between risks and needs in this context. So the COMPASS score, which is one of the most widely used models in the US, has a set of predictions for what it calls risks and a second set for what it calls needs. So risks are things like your risk of committing another crime, your risk of not showing up for your trial. Your needs might be something like you have a drug dependency issue, or you don't have a strong family environment, or you might be homeless, et cetera. And the way that the tool is designed, it tries to make very clear the difference between the things which are essentially punitive in nature and the things which are really just reason for society to want to help that person more. If they're risky of committing crimes, then perhaps incarceration is, a way to address that. But if they don't have a strong supportive family environment, or if they have drug dependency issues, that's not a reason to incarcerate the person. That's a reason to provide them additional services. And so they've designated these with red and green. And yet, in practice, many judges actually just treat this as all the more reason to put a person behind bars. And so there's an additional kind of human-computer interface question here between what the model is purportedly predicting and the way that those predictions are being used in practice. I think actually this ends up being one of the most critical areas. So for example, if you are predicting that someone is unlikely to appear for their trial date, the model can give you a calibrated, risk score on a scale of 1 to 10, saying this person is likely not to appear for their court appointment. Well, what do you actually do with that prediction? One of your options is to incarcerate the person. That's one way of forcing them to come to their trial. But another option would be sending them a text message, an SMS. And there's a growing body of literature that suggests that this is actually very effective indeed. And so I think there are critical questions here, not only within the model building process, but really at the membrane, if you will, between the model and society, of not only what is this model predicting, but what real world intervention is that prediction being used for? Now, we've talked a lot, basically almost exclusively over this talk, about a type of machine learning that's called supervised learning, where you're given a set of images or a set of cases in the criminal context, one by one, and you're asked to make these kind of isolated predictions, and you get feedback about each one. I want to shift the focus now for the final section of the talk into an area called reinforcement learning. In reinforcement learning, the setup is a little bit different. You're taking a sequence of actions in order to maximize some kind of score or some kind of reward. So the canonical example here would be something like Atari, learning how to play an Atari game, where you might have to take a number of different actions and get to a certain part of the screen or whatever it might be, and then you receive some reward in response to that entire sequence. Now, the field of reinforcement learning has made some incredible progress in the last 7 or 8 years, not just with video game playing, but with board games like Go, with robotics, which are now sort of staggeringly dexterous compared to even just a few years ago, and also with self-driving cars. I think many of these examples will be familiar to people who think about AI, but I think it's less well appreciated how much reinforcement learning has come to be adopted in commercial tech products. So for example, Facebook released a white paper in 2018 talking about adopting this reinforcement learning model called DQN to do their notifications. And I think it's very interesting that they're moving to this reinforcement learning model of, not only do you want to send someone a notification that will make them click, But if you think about it in a temporal context, you don't want to send them so many notifications that they burn out and then turn notifications off. So they've now moved to this reinforcement learning model. And in fact, they use the exact same model, DQN, which was developed for use in these Atari games. So I think there's something very ironic here that from a computer science perspective, we are the video game that social media plays. It's literally the exact same formal model. So what does the alignment problem look like in the reinforcement learning context? Well, it all comes down to how do we specify these points? What is the so-called reward function that we want our system to maximize in order to get the behavior that we want? It might sound simple enough, but this is actually very complicated and full of cautionary tales that almost any researcher has. So one of the classic examples here, this is from a boat racing game called Coast Runners 3, I think. OpenAI was developing a system to play this game, and they, like almost any research team, just used the in-game score as this reward function and said, do whatever you need to do to get as many points as possible. And they assumed that this would correspond with, actually winning the race, because it is a racing game after all. But to their astonishment, their program found this little harbor where it could just spin around, and around, infinitely getting these little power-ups that would regenerate just in time for it to swing around again, ultimately accumulating an infinite number of points, but completely ignoring the race that it was supposed to be participating in. And this turns out to be an absolutely chronic problem in reinforcement learning. There's a number of issues here that come up even in the video game settings. One of them is what's called sparsity, which is that if your video game doesn't give you points often enough, then your machine learning system isn't going to know whether it's on the right track or not. And there's a whole tangent we could go on here about the way that machine learning researchers are turning to developmental psychology and cognitive science and borrowing ideas from what we understand about how infants play in order to make progress on some of these reinforcement learning tasks. But staying specifically on this alignment question, designing this reward function well turns out to be extremely, extremely difficult. So there are several cautionary tales here that I think really illustrate this point. The first comes from a group of Danish researchers that were developing a reinforcement learning agent to ride a virtual bicycle to a destination. So that includes, staying upright, staying balanced, etc. And they decided to give the program some reward for making incremental progress toward the destination. So anytime it moved, 1 inch toward the destination, they would give it 1 point. Well, they missed a critical loophole. And so it's worth taking a second to figure out if you can predict what their agent ended up doing. What it ended up teaching itself to do was to ride the bike in circles as quickly as it possibly could, because 50% of the time it was going toward the destination and accumulating points. And then the other 50% of the time was just resetting, and then it would get more points, and then it would get more points. They had forgot to subtract progress away from the goal. And they ended up with a behavior that they didn't expect and they didn't want. A similar thing happened to David Andre and Astro Teller, who is now the leader of Google X. They were developing a robot to play in a soccer competition. And they thought, okay, well, it's going to be very difficult for our robot to learn how to score goals. So let's give it a little bit of incentives along the way. So we'll give it a 100th of a point every time it takes possession of the ball, because that's kind of a necessary precursor to scoring goals. Well, unfortunately, what their robot learned to do is to approach the ball and then just vibrate its paddle as quickly as possible, repeatedly taking possession of the ball and earning an infinite number of points. It was much easier to do that than to learn how to actually play soccer. So stories like these have led many people in the field to conclude that manually designing reward functions for reinforcement learning agents is simply never going to be safe. You can never anticipate all of the incredibly clever and subtle loopholes that these programs will find. And once they find them, they will exploit them. So what else might we do? Well, there's an interesting movement within the field to get beyond this question of manually specifying the reward function for our system. One of the ways of doing that, well, we'll come back to this. So one of the ways of doing that is to, rather than telling the program what good driving might look like, you simply have it imitate the way you drive. Now, this is an approach called behavior cloning, sometimes known as imitation learning. It was used back in the early 1990s by Dean Pomerleau of Carnegie Mellon, who was one of the earliest people to successfully drive a car on the highway and let a neural network steer the car for him. So he did this in, I believe, 1990. He drove this Humvee all the way from Carnegie Mellon to Lake Erie, which is about a 2-hour drive on the highway, using a computer running a neural network, which was, in modern terms, had about 1/10 the processing power of a first-generation Apple Watch. So if you had someone today talking about driving on the highway with a computer that was running on their Apple Watch, you'd think they were quite insane. But as long as you specify the task simply enough of just drive the way I drive, notice these little lines, and notice the way that I steer when the lines go left and right, and just do that. Don't worry about identifying cars. Don't worry about having a model of physics or understanding traffic safety or, stoplights or anything like that. Just look at the lines and then steer the way that I steer. It was enough for him to drive for 2 hours without any manual intervention. And this approach is still used today. For example, Tesla has this thing that they call shadow mode. So anyone with a Tesla, if you're driving and your autopilot is disengaged, even if it's turned off, your car is still anticipating what it would do if it were driving the car. And it is constantly comparing that against your own driving. There are many subtle problems in how imitation learning can go wrong. We can get a little bit deeper into that in the Q&A. But one of the basic ideas is this question of distribution shift. So if your system is learning from an expert driver, then there's this problem which, as soon as the system makes a mistake, it might find itself in a scenario that it has no data about because the human driver never made that mistake. And so this can lead to what are known as cascading errors and essentially catastrophic failures. There are a number of computer scientists that have been working on this, including Stefan Ross from Waymo, Drew Bagnell from Carnegie Mellon, working on the computer science side. But I think there's also a very, very fascinating intersection here between the computer science of imitation and some questions that have been longstanding debates in ethical philosophy. For example, philosophers Holly Smith and Rosalind Hursthouse have talked about this question of, if you have some sort of ethical role model, do you always do what they would do, even if that puts you in a situation where, because you're not as good of a person as them, it will then lead you to do something bad? So these are active debates that have been going on at least since the 1970s. And it has been very fascinating to see that longstanding controversy now making its way over into computer science. The last thing I want to talk about is something called inverse reinforcement learning. So rather than explicitly specifying what the objective that a system should be, what if the system watches us and figures out what it thinks that we're trying to do? So this turns out to be a capacity that is very deeply rooted in human beings. The cognitive scientist Felix Warneken has shown, for example, that if you hold a stack of magazines and bump into a cabinet as if you're trying to put the magazines away, but you don't know how to get the cabinet open because your hands are tied up holding the magazines, children as young as, I think, 18 months in this case will toddle over, open the doors, and then look at you expectantly saying, "How's that?" And this is before theory of mind, right? Theory of mind develops at around age 4. So years before we understand that other people have different perceptions than we do, different beliefs than we do, we still have this very deeply rooted capability to understand what it is that people want and what they're trying to do, and this very deeply rooted instinct to help them. So there's been a movement within computer science to basically develop the same thing for machines. And there's been work by, for example, Peter Abeel of UC Berkeley, to develop systems that in a driving simulator can figure out that good driving means keeping a safe following distance. It means keeping to the left-hand lane unless you want to pass. It means, trying to obey the speed limit. And once it realizes that those are the goals that we appear to be motivated by, then it can take over and pursue those goals itself. This has led to some really signature successes in the field. For example, in helicopter stunts, Abeel and his collaborators have shown that you can attempt to do helicopter stunts using a remote control joystick. And the amazing thing is, even if you're unsuccessful, or even if you're kind of, mediocre, the computer model can figure out what it thinks you're trying to do, and then it can go do that stunt better than you yourself could do it. This is now moving into yet a new generation of roboticists, for example, Chelsea Finn at Stanford, who have been able to take this into some pretty amazing directions. So here she is demonstrating putting dishes away in a dish rack, and the robot is able to figure out what she's trying to do and fill the rest of the dish rack. I think it's pretty incredible, and we are really moving away from the domain of computers only being able to do the things that we can explicitly tell them to do and specify in the language of numbers and code. So the last thing that I want to touch on here in the research is this question of, okay, there's an increasing body of research that shows that computers can understand what we're trying to do when we can demonstrate it. But there are a lot of things in life that we can't actually demonstrate personally. And we certainly can't specify in the language of mathematics, but we would know them instantly if we saw them. We can recognize it when we see it. Might there still be a way for getting a computer system to be able to get the picture of what we want and to do that? Well, there's this work by Paul Cristiano of OpenAI, Jan Laika from DeepMind, where they had an idea where they would just show video clips to people. They would show a pair of video clips and say, which of these two video clips is closer to the thing that you want to see? And in the background, they would have this reward model that was trying to figure out what it thought you wanted based on these different preferences that you're making. And then it would try to optimize for that. And then it would show you some new a new pair of videos. They used the example of a backflip. So they thought, if you had this virtual robot and you wanted it to backflip, well, it'd be very hard to demonstrate a backflip yourself. It would be very hard to even perform a backflip on a game controller. And it would be very hard to specify a backflip in the language of the torques on the joints and the rotational inertia and all of these things. But if you saw a backflip, you would recognize it. And so they started showing people these video clips of the robot just writhing around at random. And they said, which of these looks slightly more like a backflip? And after about 1 hour of this, suddenly you have the following thing, which is the system is performing these kind of perfect gymnastic backflips. It's tucking itself in order to spin faster the way that a figure skater would. It's sticking the landing. And not just this, but every person that participated in the study ended up with a slightly different backflip, as if they all had a different aesthetic sensibility or a different platonic backflip in their mind, and the system was able to find it. To me, I think this is one of the most hopeful results in the whole field, and it really suggests to us that there may be a way to get some of these high-level human desires and concepts into these systems, even when we can't articulate it mathematically, even when we can't demonstrate it. There still might be a way for the system to essentially extract that information from us, just through our preferences and our choices. And I really love the sentence that they used in experiment. You can see it in bold here. It says, look at the clips and select the one in which better things happen. And I told Jan Leica that I loved how general that was. There was something almost lyrical about it. That it suggested, of course, many technical hurdles have to be dealt with, but it suggests a world in which we see video clips and we're asked to pick which one shows the better, more harmonious society or the more ethical behavior, and really the sky's the limit. And he said, of course, this wasn't about backflips. That's exactly the idea. So to conclude, I think that solving the alignment problem really will be the defining human project of the decade, if not the century, as we turn increasingly large portions of our society over to these systems that are learning from us by example. I think we have every reason to be concerned as well as encouraged. This is really a kind of philosophy on a deadline, some people have said. But we really are, I think, rising to meet the moment. And if we can do that successfully, I think the results will be profound, and it will be really a revelatory encounter with ourselves. Who are we as a society? What do we value? What are the things that we want? My mind keeps going back to this 1952 radio address by Alan Turing, where he was part of a panel of scientists talking about machine intelligence. And he starts talking about the problem of machine learning. And he says, I've been doing some experiments in trying to teach a machine to do something very simple. And a great deal of intervention was needed before I could get it to learn anything at all. It kept going in the wrong direction, learning the wrong thing, not learning fast enough, not learning what I wanted it to learn. I had to keep intervening and keep adjusting it. And his fellow panelist jumps in and says, well, Turing, who is learning though, you or the machine? And Turing responds, well, I suppose we both were. Thank you.
Wow, thank you so much, Brian. That was absolutely fascinating, and lots of people have been saying as such in the chat. I think I described that talk as clear-eyed. I think sometimes when we have AI speakers, they're either like, AI is amazing, it's going to solve everything, it's going to be brilliant, and we have other people who are like, AI is terrible, it's going to destroy the world. And I think you struck a really nice, realistic, hard-nosed kind of balance between the sort of costs and benefits of this technology. So thank you so much for that, and just some fascinating examples. We've got some great questions in the chat, so please do jump in and contribute to the discussion if you can. I'll just kick things off with a question of my own, actually, using my privilege. I was going to talk to you about A-levels. Do you know what A-levels are, and are you aware of the A-levels?
I know that it is a test that people in high school take, right, to get into university.
Correct. So at 18 in the UK, you'll take your A levels, and that will qualify you to go into university. And of course, in 2020, that didn't happen. So what the government did instead was it used an algorithm based on students' previous grades and various other factors, and then predicted what they would have got in their A levels, and then those were the grades. Now, unfortunately, one of the things that the algorithm took into account was what kind of school you went to. So for someone like myself, I went to a pretty ordinary school, but there are sort of levels of schools. There are grammar schools that you have to take exams to get into. There are private schools you have to pay to get into. And there are some schools like Eton that you have to pay and take an exam to get into. And so obviously those people that are at the more high achieving schools were then predicted these higher grades. Whereas people like me would have been sadly disadvantaged by this algorithm. I just wondered if you sort of comment on that story, because it's similar to the justice example, and just this idea of applying averages. So like on average, sure, people that went to my school would have done worse than people who went to Eton. I'd totally accept that. But when you then shrink that down to the individual and say, okay, this child now is predicted, 3 C's when they would have got, maybe could have got 3 A's, or maybe could have got 3 E's. I just wonder if that's a sort of related issue to the criminal justice issue.
It is. I mean, there are a number of intersections there. I mean, it's so problematic on its face that you question whatever decision-making process led that to actually happen. But I think there's a number of kind of subtle points here as well. I mean, there are many things ranging from the use of automated scoring for essays, which I think is a lot it's sort of problematic in its own right to kind of codify explicitly, these are the types of words that good essays contain, and if you have more of those words, then your essay is scored more highly. I myself taught creative writing in the University of Washington for many years, and I think anyone who has studied the history of art knows that the greatest artists have been the very people who have broken the mold, right? Beethoven's First Symphony, I think, begins with a seventh chord that was so dissonant to audiences at the time that people just walked out. And those are the moments that sort of move society, move the arts forward. Is particularly when you break that expectation, break that model. So that's one thing. I mean, I think there are a lot of really complicated questions here in what features go into the model as input, and what can the model infer anyway. So I use the analogy in the book of something that happened to the Boston Symphony Orchestra in the early 20th century. They were worried about gender representation. Basically, the symphony was all male. And someone had the idea of, well, let's start holding auditions blind behind a screen so that we can't, be biased whether someone's male or female. This failed to improve the representation of women in the orchestra until someone realized, had the additional insight that they needed to instruct people to remove their shoes. Because as the auditioners walked out onto the parquet wood floor, it was completely obvious to the people, even though they were behind a screen, whether the person was wearing high-heeled shoes or flat, men's dress shoes. And I use this as an analogy in the book to think about machine learning. So there are a lot of cases where the law, at least in the US, civil rights law in the US defines these things that are known as protected attributes. And you are generally not allowed to make a decision on the basis of those protected attributes. The problem is that these systems are awfully good at predicting those attributes, even when they're not told them directly. And so that's the first problem. The second problem, so you can say, oh, well, this model can't possibly be sexist because it doesn't know the sex of the applicant. All it knows is that they played field hockey, or they played lacrosse, or they played football, or whatever it is. Or they wrote their CV using these words. It turns out that any of that is more than enough for the model to infer the sex of the applicant. Secondly, there's this very counterintuitive point that was first articulated by Cynthia Dwork, a computer scientist at Harvard, called fairness through awareness, which is basically making the argument that in some cases, the only way to mitigate a harm is to know that particular attribute. So, for example, in Manhattan, white and black people self-report that they use marijuana at the same rate per capita. But black people are 15 times as likely to be arrested by the police for marijuana. So if you had someone, you're considering them for a job or for parole or whatever it might be, and it says this person's been arrested 15 times for marijuana possession, you can imagine making the argument that it would be more fair to know their race, because you could say, oh, well, it's a black person, so that's mentally equivalent to a white person that's been arrested once. Right, but that sort of thing is only possible if you have access to the feature. And so that's a whole other kettle of fish. I've talked to many engineers at big tech companies who have said, my management tells me that I need to make sure there's no bias in my model, but they also tell me that because of GDPR or because of different things, I don't have access to the actual underlying data to know whether the model is biased or not, and yet I'm still expected to make sure that it's not. So I think there are some issues there that I would say the law still has to catch up to the actual computer science.
Yeah, absolutely. Right, I'll crack into the questions. So Ask McNeil asked a question just saying, if an algorithm produced by an AI is found to have an inherent flaw, so for example, the discrimination, for example, would you then can you just correct an algorithm? Can you then add in that race data and subtract it in some way from your final decision? Or do you have to kind of scrap it and then start all over again?
In some cases you can, and there are different model architectures that make that easier or harder. I think the big problem for many people is the unknown unknowns. What's in the model? If it believes these things, what else does it believe that we don't know about? So one example I give in the book, there was a study done in Pittsburgh about pneumonia and trying to build models to predict whether pneumonia patients should be held overnight in the hospital or released to go home. And there were a number of different teams competing, and the model that won was this, big neural network. And yet the very people who designed that big neural network, essentially pled like, please don't actually use this in the hospital setting. And the reason they did that is that one of the simpler models used something called a rule list, which is basically these sort of if X then Y rules that the model learned. One of the rules that the model learned was if the patient has asthma, they're probably going to be fine. And we should send them home. And that just didn't make any sense, right? So it's just intuitively obvious if someone has pneumonia and asthma, that's worse than if they just have pneumonia. But the correlation was real in the sense that if you looked at the data set, the asthmatics did slightly better on average than the non-asthmatics, but that was only because they were treated as such high priority patients by the hospital. They received the best care, which is precisely the care that the model, of course, would deny to those patients. But I interviewed Rich Caruana from Microsoft, who had developed the neural net, and he said, I wasn't worried about the asthma thing because we know about that. So, okay, I can go and fix that and delete that. The problem is that the neural net, precisely because it was better in this competition than the rule set, learned things that aren't in the rule set. And so we don't know what else is in there. And actually, he went back 20 years later and looked at the model with contemporary interpretability tools, and he was able to find like, oh God, yeah, it thinks being over 100 is good for you. It thinks high blood pressure is good for you. It thinks chest pain is good for you. Thank God we didn't ship the neural net. So I think that is a story that is coming up again and again.
You touched on something interesting there, which is this idea of explicability. And I feel like I've heard about legislation around this as well, this idea that the AIs and algorithms shouldn't just be a black box, that nobody knows what the hell it's doing, but there should be a way of, like you say, unpacking it and going, oh my God, it's saying chest pains are great. And I just wondered, am I right in thinking there's been some move to try and legislate this to make sure that people aren't just given a random answer from a black box?
That's right. Yeah, one of the people, in fact, that we meet in the course of the book is Bryce Goodman, who's a researcher at Oxford Internet Institute, who is going through the draft version of the GDPR and came across this line that said something to the effect of, if people are adversely affected by an algorithmic decision, they have a right to an explanation of what happened. Mm-hmm. And he took it to his colleague at Oxford, who had a machine learning PhD, and he said, correct me if I'm wrong, but this is like an unsolved problem in the field of machine learning. And his colleague said, yeah, it is. And I've spoken with some lawyers from big tech companies who went to the EU regulators and said, you do realize that you're making a legal requirement something that is an unsolved scientific problem. And the regulators were unmoved. They said, well, that's why it doesn't go into effect for another 2 years. So figure it out. Which I think is an interesting anecdote in itself, because it points out that we think of regulation as exclusively stifling scientific or technological progress. But in this case, there was a huge frantic effort to develop these explanation methods precisely because the legal requirement existed.
Just going back to the medical example, you obviously told us a few examples there of medical algorithms and AIs going wrong. But RP asks, can you provide examples where predictions are actually accurate and beneficial? So one example he gives is medical diagnosis, especially when the disease was overlooked by humans. I think they get AIs to sort of scan, X-rays and so forth. And is it true that they're now kind of generally performing as well, if not better, than professionals?
Yeah, there are a lot of success stories in medicine. For example, in dermatology, at developing models that can detect whether a discoloration on the skin is malignant or benign. We meet a dermatologist who had a patient with this strange mark on their arm, and the dermatologist wasn't sure. It was really borderline. It looked like it was probably fine, but there was something felt off about it. And he had been working on this research study with the computer science folks. And so he pulled out his smartphone and he started taking pictures of the patient's arm. And even though it was very ambivalent, very borderline for him, every single picture he took, from every angle with every different lighting condition, it came out malignant, 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 malignant. And so he sent it to one of his colleagues and he said, check this out. They got it biopsied or whatever. And they were like, wow, this is one of the earliest stage things that we've ever caught. And so there's a lot of really, really encouraging results there. But I think even there, it is important to have a kind of a sober note of caution. So that same dermatologist ended up writing a letter in like the Journal of Dermatology arguing, just because we've had these success stories doesn't mean that we should just rush to deploy these things, because they started using these kind of interpretability methods, and they were looking at what are some of the things that most strongly this model is looking for when it identifies something as cancerous. And it turned out that the thing that it was most looking for was a ruler, because medical textbook images have a ruler for scale.
Amazing.
And so it thought that the presence of a ruler indicated that something was cancerous. So, I mean, it's again, the correlation is not wrong, but it's not causal.
So while we're on life and death decisions, there was another question about the military. Are they using machine learning for targeting systems, weapons, identifying friend and foe? And obviously, it doesn't take much imagination to think how that could go horribly wrong.
Absolutely, they absolutely are. And in fact, the military has been one of the biggest drivers and funders of interpretability, explainability research. So I interviewed some people at DARPA, which is the U.S. Defense Advanced Research Project Agency, and the intelligence community a few years ago were starting to have exactly this problem. So people would get these reports saying this grainy satellite photo has been identified as a missile silo or whatever. And so, sign on the dotted line and we're going to blow it up. Or, I mean, I'm oversimplifying it. But the point was that they had to actually put their name on it and they had to personally authorize it, because that's the way that the agency functions. And people were becoming increasingly uncomfortable saying, well, I'm putting my name on this. There are going to be real world impacts, but I don't know what the model thinks it sees. And so that led DARPA to initiate this multi-year project called XAI, Explainable AI, where they were funding a number of different groups. And so that has been actually one of the big drivers, is this feeling of personal accountability to these decisions, which I think is a good check. I mean, thank God we don't just automate the entire pipeline and just blow the stuff up automatically, right? But the person who's in the loop wants to feel comfortable that they understand what it is that the model is actually seeing.
It reminds me of the film War Games, if you've seen that one.
That is the only winning move is not to play.
Not to play, yeah.
Yeah.
About a mutant AI that's going to destroy the world. So there are a few more philosophical questions that came up, which I just thought I'd put to you before we wrap up. So Sean Meads had a very lengthy question, but I think the gist of it was the idea was this idea of AI showing human values, consideration, expect, and this idea of AI replicating the brain in some way. And to what extent are these AIs just specific tools that we're just using for a specific task to, I don't know, recommend movies to me on Netflix? And to what extent are we actually trying to, recreate a human brain that can, experience love and have consciousness and all this kind of stuff?
It's a very big question. I'll give one of my favorite stories here. So there's this concept in reinforcement learning called TD learning, or temporal difference learning. And the basic idea is, let's say you're developing a program to play Go or to play chess or whatever. It has sort of a running count of how likely it thinks it is to win the game. And if you make a move and then all of a sudden think, oh, shoot, now I'm probably going to lose. You don't need to wait until you lose the game to get information. So you can use what's called this temporal difference error of, a moment ago I thought I was fine, now I think I'm toast. You can use that as a learning signal. And so this has been very useful within the field going back to the early 90s. Separately, there was a bunch of advances in the 70s and 80s on like like the ability to actually observe in real time individual neurons in the brain, and in particular dopamine neurons, dopamine neurons presented this real mystery where they appeared to correspond to rewards, but not exactly. They appeared to correspond to surprise, but not exactly. So there was this huge question mark over what role was dopamine playing in the brain. The data were very mysterious and no theory perfectly matched up. Well, once the reinforcement learning community got a hold of those data, they were like, oh, the brain's doing TD learning. And it turns out that this is the accepted story of the role of dopamine in the brain to this day. And so to me, I think there is a lot of very strong evidence like this that we are, in some cases, directly borrowing from cognitive neuroscience to solve things in reinforcement learning. In other cases, we're independently inventing something that then turns out to be the formal model to explain what's going on in the brain. So all of that to me suggests that we are indeed not merely developing engineering solutions that solve particular problems, but that we are in fact finding some of the canonical laws of intelligence, period. The same exact things that evolution itself has found.
And also the same exact thing that Alan Turing said in his quote, that creating these things is teaching us about the brain as much as, as much as we're teaching it, how to learn. K.A.P. Walsh had an interesting point, which is how can the natural evolution of humanity's moral compass be taken into account with machine learning without the intervention process affecting that evolution? I suppose you made an AI in sort of, I don't know, 1820s Alabama, it would think slavery was brilliant. Whereas we don't quite think that now.
Yeah, that's right. So that's really important, and I think that's coming to be more and more appreciated within the AI community. So I mean, if you think about the alignment problem as imbuing into a system all of our norms and values, well, the last thing we want to do is lock 2021 values into a system and just let it run the world forever, right? For exactly this reason, right? If we had the aligned AI of the Middle Ages, I think it would be a nightmare. And
it'd be very superstitious as well, I think.
That's right. That's right. And you see this even at at the scale of individual years. So I'm thinking that Princeton computer scientist Arvind Narayanan has pointed out that a lot of the world's financial systems are still being run on, Pascal and COBOL and these ancient programming languages that, no one can even program anymore. And he said, imagine the equivalent in machine learning. Like we have this narrative that technology is moving so fast, we can't keep up. But in some ways, it's the opposite, right? We're running on critical infrastructure that was written in 30, 40 years ago. So imagine training a model today and having it still in production, in the 2060s. That would be, again, a nightmare. And you see this even on an individual year-by-year basis. So one of my favorite stories was a group of computational linguists that were trying to reproduce a paper that had come out that showed that a particular model had a very good accuracy at kind of predicting a missing word in a sample of text. No matter how hard they tried, they couldn't match the accuracy that the original authors of the paper had gotten. So they first thought, well, maybe there's a bug in our code. Then they thought, maybe the authors had some secret sauce that they weren't sharing. No, it wasn't any of those things. It was simply that the original paper was written in 2016, and they were trying to reproduce it in 2017 by scraping all this text off of the web to train their model. And just the things that people were talking about slightly changed, but over that 1 year period. And then you try to train the same exact model in 2018, and it's 1% worse and 1% worse. And so it really is a reminder that I think it's intrinsic to building safe AI that we very much leave the door open for it to continue to learn, right? I think it is it's folly to develop any system, no matter how carefully, and then just kind of seal it off and say, you're in charge, right? That constant process of checking back in and making sure that reality continues to match your expectation, I think is totally essential to human and machine decision making.
So I think probably got time to squeeze in one more question. Oh, they're all so good. I don't know which one to pick. So I'll pick this one, which is, are there any known cases of AI used for fraudulent purposes? So one thing that I came to mind with me is when humans try and do fraud, we'll often do stupid things like not realize Benford's law exists, so that when we're making up numbers for our accountants, our cooked books, it's something that could be quite easily spotted. But are there ways that AI could sort of more, what's the word, authentically commit fraud or other things?
Yeah, I mean, in a funny way, this takes us back to the subject of my talk a decade ago at the Royal Institution
Yeah.
about the Turing test. That we are now living in, I think, a very uncanny world with respect to the Turing test, where starting in late 2017, there has been a revolution specifically in language models. So there's this new generation of language models called attention models or transformer models. The most well-known of which is probably GPT-3 at this point, which has, I think, about 1/1000th the parameters of the human brain, depending on how you estimate that. So, there's only so many more powers of 10. So 1/1000th, I think, is quite breathtaking in that sense. And these models are incredibly virtuosic at producing text, right? So you can give it a prompt like, give me a news article about a Peruvian explorer who finds a secret tribe of talking unicorns in the Andes Mountains that speak perfect English. And it will just give you this, reasonable journalistic prose. Dr. Javier Garcia discovered, through his trek through the such and such and such, it will quote the person. It will, it adopts the sort of journalistic conventions around sentence structure and paragraph length and all these things. That technology, that sort of chameleon-like ability to produce reasonable, plausible text in almost any form, in response to almost any prompt on demand, I think is setting us up for a crisis of authenticity in terms of, online discourse. So I'm very, very, very curious to see how public forums like Twitter, like Reddit, are going to survive the ability to produce human-like speech at scale, for pennies, right? And not merely speech that seems human-like enough to kind of get past most people's filters, but that has some kind of worldview, right? You can tell it to constantly make arguments that are sort of pro or anti-EU or pro or anti some corporation or, whatever. And it is not yet clear to me how we are prepared to deal with that. So I think that's going to be one of the major challenges of the next few years.
I mean, my thought is it's going to be captures all the way down, isn't it? Every time you log into any website, you'll have to be solving these tests, and they get more and more intricate as AIs get better at solving them, and then us humans have to get better at.
Well, that captures are themselves a very eerie nutshell history of the entire progress of AI. So the acronym CAPTCHA is a completely automated public Turing test to tell humans and computers apart, something like this. And so it is a Turing test. It's part of the acronym. And someone did a remarkable study on how difficult CAPTCHAs have gotten. So the average CAPTCHA in like 2008 took 8 seconds to fill out, and now it takes like 30 seconds. And as machines keep getting better, the cognitive load required to successfully complete a CAPTCHA is just going to go up. And so what's the end game of that? The further irony is that most of the CAPTCHA data is being collected by companies like Google and used to train computer models. Like the reason that you have to click on pictures of stop signs or hills or buses or whatever is because it wants to automate the ability to recognize those very things. So, from an American context, this is, I think about like the Miranda rights that get read to you when you're arrested. It's like, you have the right to remain silent. Anything you say can and will be used against you. So the very act of filling out a CAPTCHA is, giving the very data to the machine that's going to automate that exact task that you're performing. So it is absolutely an arms race, and I'm not at all clear where that ends.
I know we're slightly over time, but I've always wondered about this. So I did know that obviously when you click on stop signs, it's telling Google, what stop signs are. But then how does it know you're right? Or does it sometimes check your answer with somebody else, and sometimes you just click anything and it's fine because it hasn't comparing it to any answer out there?
So some of them are have already been answered by other people.
Yeah.
And it's checking to make sure that you give the same answer that the other people gave. And then others, and of course you never know which, are sort of novel, and it's just asking you what you think, and it might let you get through no matter what you say. And again, this goes back to the question of truth versus consensus, right? We're not training our models to identify what a school bus or whatever really is. We're training it to match the judgment of random people on the internet with better things to do who are being very impatient. So we'll see where that takes us.
Well, that's probably a great note to end on. Thank you so much, Brian. That was absolutely fantastic. And thank you to everyone in the chat for your brilliant comments. I've just got a few things to say before I wave goodbye. Just a reminder, anyone in the world is welcome to join as a member or patron of the Royal Institution. You get a lovely membership card. You get to say, I'm a member of the Royal Institution, don't you know, to all your friends, which is great. And many other benefits besides. If you've enjoyed the stream, please do donate £10 or more. I can't stop you donating £100 or £1,000 if you want to. But as a charity, we'd much appreciate it. And of course, you can buy the book. The Alignment Problem is available in multinational corporations and also from your local bookstore. So do please go and check it out. Would really appreciate if you fill in our post-event survey, which should get sent around to you. Also, do not forget, on Tuesday, we've got Rohin Francis, some of you might know as Medlife Crisis on YouTube, talking about pushing the human body to its extremes. And then we've got Mark Solms on Thursday, delving into the mystery of consciousness. So that's about it from me. Brian, just before we go, if people want to get in touch or want to find out more about you, do you have a website, Twitter, or anything you'd like to plug?
Sure. Yeah, it's brianchristian.org, and I'm on Twitter @brianchristian.
Fantastic. Well, thank you so much, Brian. It's been a brilliant evening, and thank you all for your questions, and we'll see you again soon. Take care.